Okay, it is really important that you be on time. If you are, I don't know, 30 seconds late or something, it doesn't ever really affect me. But once I've taken the roll, and then if I have to go back and take the roll again, it does kind of slow things down. So I pay incentive to reward you to just kind of try and get the habit of being here on time. So I think I don't know if I had time. Did I explain the famous footwear coupons last time? Yeah. Okay. So this is 0.1% of your grade. So if you are on time today when I walk by, I'm also practicing your names. So as I go by, just kind of give some sort of signal that you're on time. So Liza Calhoun, yes, and Ellie Wagner, yes, and August Sunderledge, and Clark Pugh, and Spencer Smith, Noah Norton. Shoot. Trey Robinson. And it's Maddox Moss. Yeah, I was going to say, I knew it was a double M or something. Yeah, Maddox Moss. TJ Sessions, yes, true. Marion Dewey. Zach Richter.
I think it's called
Sarah.
Sarah.
You got it.
Yeah, Jared. Yeah, I think it's like in the US.
Riley. Diesel. Lincoln Young. Josh. Hughes.
Yep.
Jared. John. Frank. Caleb. You were talking about that.
Yeah.
What's up?
Only like 3 minutes.
Are your glasses easy this year?
And I know third, like first would be half.
Last year you had a lot of
Oh. Aaron Park. Don't say that now.
You did start on Wednesday.
I wanted to ask you. I was so confused. I was like, wait, is that you?
Last year? Oh, no, you
That's
should
you.
have done it. So did you get it? Yeah, when you it's only fast. Or when we did house. Weekend of the and then so you're taking really? Sounds about right.
Only for Dean.
Good. Parker. Grace was. Taylor. All right. So another thing. Hey, listen. Okay. I try to, pretty consistent, rare exceptions, always have some sort of video that records the discussion that we have in class. I don't do it for every single period. I'll usually pick one period and make a video for discussion, even though every period's discussion can be a little bit different. And then I will get that posted on Canvas. That's not really a great substitute if you're not here, but it's better than nothing. So anyway, so this is now recording, so you're all live and whatever. So the microphone's over here. So it doesn't record a video, it just is like, just records what I write on the board and what the audio in the room. So, okay, a lot of what we're doing now is just kind of getting used to my style. I try to be fairly efficient, and so I don't, how do I say, I don't usually pass out like a note packet. I usually just have like one packet that is homework problems, and then we just kind of pick selected problems to talk about from the homework, okay? So that's what that is. One other thing, I have two different pairs of glasses, one for when I'm sitting in front of the computer and one for more regular use, and I have the wrong pair on. I'm like, why is the back of the room blurry? This should be better. Okay. All right, we're going to jump right in. The first year I taught calculus, I actually spent about a month reviewing, doing things that you had done in previous classes. And what I discovered was it was really boring and it really wasn't that helpful. Like once we got to places in the year where we needed that material, people didn't really remember it any better having reviewed it during the first month. So I decided that's kind of a waste of time. So we jump right in. So today we are starting calculus. And the very first topic is limits and continuity. And so we're going to start talking about that. A key thing in my room, I talked about this last time, like everybody look at me. The level of concentration just has to be what you feel now. Like when you're all like really with me, we're all together. But another thing that I want to try and create, and I've usually been very successful at this, is just getting you to be so comfortable with the discussion that you're not reluctant at all to ever just say, whoa, wait, say that again, say it different, whatever. You don't have to have a question to raise your hand in my class. Like you just have to have a willingness to say, I feel kind of lost, or I don't really get it, or whatever. Like just stop me and just talk. Sometimes it's really hard to know how to phrase a question, but if you'll at least just kind of stop and talk a little bit, we'll figure it out. The other thing I'll do is I will do a lot of things to elicit your participation. I'll kind of explain that as we go. So this is just the very first problem in this packet. It says use limits to analyze the continuity of the function at 4 different x coordinates. Okay, huge thing in this class. And you've been doing this for a lot of years, you just may not have noticed. Whenever we talk about any problem, we are always talking about two numbers, never one. Like it's always a comparison between two. What I mean by that is like, okay, this is a graph. A graph is just a picture of a whole bunch of number pairs. For example, we'll just do some easy ones here. They're all pretty easy. So if I go to this dot, okay, every dot on a graph is really representing two numbers, and it's always two numbers. It's never one. It's always representing two numbers. So I want to get a lot of participation. This one's super easy. It's just a way for me to pay you. Extra credit, all of you are going to take one of these flashcards. I just leave them on the table so you have access to them. And you're going to just keep one of them with you. And you're going to keep track of tally marks. Like how many times I say, hey, you earned a point, hey, you earned 2 points, you earned 3 points, whatever. So, for example, I'm looking at that purple dot. I know that purple dot represents two numbers. It represents an x value and it represents a y value. Super simple. We're just practicing how to get points here. So don't say it out loud, but raise your hand if you know what x value and y value appear to be, kind of make an estimate there, represented by that purple dot. Okay, so here's how the tally marks work. If your hand is raised, you mark down one tally mark. Just right now, just mark it down. And we'll call on Taylor in the back. So what is the x and y pair represented by that dot, Taylor?
1, 2.
Try again.
1, 3.
There we go. Does that make sense?
Yes.
Cool. No worries. So Taylor gets 2 more tally marks for being the voice. So mark down 2 more, Taylor. So we get the idea of how the tally marks work. Once you have 10, that is 0.1% extra credit on your grade. And eventually I have this, it's kind of just a tradition. There's not really any need to do this, but I literally will come one day in the near future and say, hey, it's time to trade in your tally marks for tickets. In August we'll say I have 12, and I will promptly hand him 12 tickets. And he keeps those until the end of the term, turns those in for extra credits. So, questions? Oh, please.
Wait, so you said each one is 0.1.
So each tally, it's like money. So 10 tallies is 1 ticket. 10 tickets is 1%. That makes sense? Perfect. 2 more for Zach. Mark them down. I worked really hard to get this idea that you can talk about anything. And so the standard joke in my room is like you raise your hand and say, hey, can I go get a drink of water? Yeah, mark it down too. Okay, this is really true. I get kind of carried away. Okay, And as I get your names better, we'll start paying for me for getting your name, but I can't quite pay for that quite yet, but we're getting close. Back to this, okay? I told you I like the dog, Doug. I distract easily, so. Okay, so everybody good here? Awesome. So again, don't forget it's always two numbers. It says use limits to analyze the continuity of the function. So on your paper, you're going to write the following. And just kind of in this first box where we're talking about x equal -1. Actually, back up on that. Don't write anything yet. Just kind of watch me and then I'll show you what to write in a minute. So don't write anything, just watch. I'll give you plenty of time to catch up as far as notes. So let's see. It says use limits. Raise your hand if you've heard the mathematical term limit before. A few people, okay. And when we go to talk about a limit, you have to use the proper notation. So the abbreviation is simply LIM, stands for limit. This symbol is going to talk about two values again, an x value and a y value. So we write down the x, and we're supposed to be analyzing the continuity at x equal -1. When you're finding a limit, it is crucial that you remember that you are not thinking of x equaling -1. You are thinking of x being very, very close to equaling -1. So you don't use an equal sign, you must use an arrow. The AP graders spend a lot of time grading your work, so it's critical, I was going to say crucial, I said crucial. It's critical that you use the right notation. So make sure you use an arrow. Okay, this is currently referenced, oh yeah, please.
So it says x approaches the number?
Two more for, don't say it. Josh Ellertson.
Yeah.
Perfect. Hannah Johnson, please.
Is that notation only for when x is getting close to -1, or is it also for like at x equals 0 and x equals 2?
Oh, perfect. Two more. Mark them down, Hannah. And I will say your first and last name for a few days just so I get it down, and then I'll kind of stop doing that. But Hannah's correct. You can find the limit for any x value. So we're doing a specific example of where x is getting close to -1. We could use any of these also, or any one we chose. We could have x approaching any number we happen to be interested in. So the number doesn't matter. Anybody else?
Doesn't
Please.
sign matter? Like if it's going left instead, would it still be x approaching -1? Or would it be like switched?
Say it one more time, audience.
So like if the slope was like not on the left side, it was like on the right side going to it, maybe that doesn't matter.
Oh, I think I know. No, keep talking. Hey, no, this is a perfect example of what I want everyone to do. Is like you have some thought, like I'm not really sure, and you're not even sure how to phrase it. Don't worry about it. Like really, just raise your hand and start talking.
Yeah.
Let me see if I'm reading it right, and if not, we'll just keep talking about it. I think what you're saying is you're kind of looking at this, and you're noting that these. Okay, every time you look at a graph, it really will help if you always think of the graph as nothing more than dots. Like I don't think of a graph as a curve and a line. All I see are dots. And every dot is just an XY pair. So I think what August was saying is he sees these dots kind of going down like this, and these dots are going like this direction. Is that what you're wondering that influences the...
Yeah.
Are you wondering like the point of the arrow?
You're just wondering about the -1 versus like +1 or...
Like the point of the arrow kind of. Like does it
Like would you switch the point of the arrow?
Oh, interesting. Like would you turn it around this way?
Right.
Is that what you're wondering?
Yeah.
Kind of. Two more for August, and two for Ellie Wagnerman. No, the arrow never changes. It's always just the notation.
Right.
Is saying you have an x value, and the x value isn't going to equal -1, but it is going to be an x that gets close. No, please.
Is that always on a graph where it's always approaching a number, never equaling a number? Or is that
Good question. Two more. Whenever you're finding a limit, you are always thinking about, it could be any value, it doesn't have to be x, but you're always thinking about a value getting close to some number. It doesn't have to be a graph. This example we're starting with is depicted graphically, but that's irrelevant. It's just saying we're going to discuss a whole bunch of XY pairs, and we're picking out one specific kind of area of the numbers. We're looking for numbers that have x coordinates that are very, very close to -1. But it doesn't have to be a graph. It could be a table. It could be a equation, whatever. So, questions? Okay, cool. So get rid of this. Okay, I said before that when we talk about it, it's always two numbers. It's always an x and it's always a y. It doesn't have to be x and y, but it's always an input, it's always an output. It's always two numbers. So right now we have one. We have the x value we're interested in is some number that's very, very close to -1. Well, when we're talking about limit, we're not talking about the x alone, we're also talking about the corresponding number pair. So we need a symbol to represent that. This says this is the graph f of x. So f of x is representing the y values. So you put here f of x, pen, come on pen. Yeah, I guess that's okay. Okay, so this symbol altogether is telling us several things. One, it is telling us that we are interested in an x coordinate that is not -1, but very, very close. And we are interested in knowing what's the y coordinate that corresponds to that x coordinate, because the numbers always come in pairs. Questions? Cool. So the next thought is, okay, if I'm looking for an x value that is almost -1, I like to think of that like a table. So here's an x value that is exactly -1. Go back to the whole room. So again, if you raise your hand, I pay you extra credit for just participating. Be honest about it. I have had people say, well, can't you just go grab tickets? I'm like, yeah, you can just go grab tickets if you want, but whatever. Okay, the test is 80% grade, so who cares? Okay. Raise your hand, please, if you can tell me. What's a number that is not -1, but you would consider to be very, very close to -1? Everybody, hands up. Don't overthink it. Don't overthink it. Let's go, Sarah Ritchie.
0.9.
So 0.9 would be a little bit more than negative. It's a little more positive than -1. So I'm going to put that right here, -0.9. That is definitely a number that we would consider to be not -1, but certainly a number that is close to -1. Okay, if your hand was raised, give yourself 1 tally mark. Sarah gets 2. When you talk about a limit, the idea is you want to theoretically pick an x value that is not -1, but is what we call infinitesimally close to equaling -1. So this is, we would think of that as close to -1. We want to be closer to -1. So raise your hand if you can tell me what's a number that is closer to -1 than -0.9. Like we want to get closer and closer and closer. Just keep picking numbers that are closer and closer and closer. And I struggle with your name. Don't tell me. Hold on. I got Jackson Bergen. Perfect. Go ahead, Jackson.
-1.01.
So that would be a little bit more negative. -1.01. If your hand was raised, give yourself 1. Jackson gets 2. This number is actually closer to -1 than this number here, but we want to get even closer. So hands up again. Like what's a number that is even closer to -1? That's what limit is talking about. It's like you're just thinking about x values that just get closer and closer and closer. Let's go, Aisel Mitchell.
-0.999 repeatedly.
There we go. So theoretically, if I think of this number here, and this is not mathematical, but it kind of helps me, I don't know, just feel like I understand it a little bit better. there is no number, like that's not really a number. Like it goes on forever, you can't really write it down. But that's the idea. That if I were to pick an x coordinate that wasn't -1, but it was really, really close, like as close as I can possibly imagine, I'm doing what the limit is asking me to do. I'm focusing on a value of x that is not -1, but it's really, really close. Okay, so if your hand was raised, mark down 1, Aso gets 2. Hannah, please.
Are we picking -1 because there is no, are we picking 0.999 because there is no y value for -1, or why would we pick that one over -1?
Oh, gotcha. So the only reason we're studying -1 really is because the problem asked us to study what's happening at x equal -1. So that's what we're following there. In this case, you are correct. At x equal -1, this particular function does not have a y value, but that's not really relevant as far as the limit is concerned. Although for AP Calculus, that's somewhat common for them to ask you what's happening at that kind of spot, but they don't have to. They'll ask you at other spots as well. Like we could have found the limit as x approaches +1 if they had asked us to do that. And that's just as valid. The question is the same question. The answer will be different. So, no, we're not looking at this particular value of x for any special reason. I don't know if that answered your question, though. Not really. Something. Keep talking a little bit.
Well, I don't know, it's just like, are we trying to find, like, a number that's close to -1, or are we trying to find -1?
Oh, gotcha. Take 3 for that one. Mark them down. No, really good. Look up, everybody. Look. Hannah said a key thing. When we're finding a limit, you have to force yourself to not pay attention to x equal -1. Like it leads to a lot of errors. Like you really have to force yourself to say, I'm not paying attention to x equaling -1. I'm trying to think of a number that's almost -1. And this number right here, -0.999 forever, isn't -1. It's different, but it is certainly infinitesimally close. Did that help a little bit? Keep going, please.
If -1 does have a y value, can you not have a limit on it?
Oh, good question. 2 more. Okay, so this is a picture of a bunch of XY pairs. We said that right here, that purple dot, the x is 1 and the y is 3. That value has nothing to do with finding a limit when x is getting close to 1. Because when we're finding a limit, we're not paying attention to what's happening when x is 1. We're paying attention to what's happening when x is almost 1. So you never want to pay attention to what's happening right at the x value. That's not related to the limit at all. Like, don't pay any attention to that. You're always paying attention to what's happening when the x value is almost that number. Did that help you?
Yeah.
Okay.
And is that?
Please.
Sorry.
No.
For the 1.01 on the x, isn't that supposed to be a positive?
Oh, that's just a mistake. Sorry.
I just didn't know.
No, keep asking. 2 more for Ellie. Yeah, just keep talking. It's the very best. Like, if we can get the whole room just talking, the more you talk, the better. I promise. Please.
So then in that scenario where x equals 1, or is it as x approaches 1, y is approaching?
In this example, that is correct. Because when x is equal to 1, y is exactly 3. But if x is not quite 1, y isn't quite 3. And that's what limit is talking about, is as the x value gets close to a certain number, what's happening to the y value. If that makes sense. And I have to pause to keep doing your name, so sorry about that. Josh Elliotson. Okay, cool. Noah, please.
I don't know if I'm the only one that's confused with what we're trying to find or solve for.
Gotcha.
Yeah.
No. Raise your hand. No, it's awesome. Hey. No, take 3. You guys are getting exactly what I want. No, I'm serious. You're getting exactly what I want. Look up. I know that it's different. Like with AP Calculus, I just can't have you, I won't help you be successful on May 13th if I just say, okay, here's a problem, here's what you do, you know what I mean? we have to spend quite a bit of time in this little bit of uncomfortable situation of just like talking about an idea, and the point is not to solve the problem, it's to just make sense of the idea. So how many feel a little bit lost right now? Just be honest. Mark down 2. Cool. Mark down. I'm serious. That's good. That's the whole idea. My goal is to give away as much extra credit as possible. I do not hide that. Let me see if I can summarize a little bit. Okay, all I've really tried to get you to do so far, 1 second, is just get a little bit of understanding about the notation. That's really it. And then I follow your questions, because I want to have you talking and you involved in thinking about what we're really doing. But we haven't accomplished anything. We're not really doing anything yet. We're just trying to understand what the symbols are talking about. Please.
Yeah, just, we're not like necessarily solving the problem right now. We're just talking about like terms and kind of just like, okay, because I don't really know what the limit was.
No, fair enough. It's brand new to pretty much everybody. And so what I'm trying to, so a couple things, I'm trying to build on the facts. Like, here, answer this. Sorry, 1 second.
You're good.
Answer this. Raise your hand if you are comfortable that when you look at this graph, it's really just a whole bunch of dots. How many are comfortable with that? Mark down 2 more if your hand is raised. Actually, everybody mark 2 just for voting. Like, here's a dot. Here's another dot. Here's another dot. Here's some more. They're everywhere. We don't always necessarily think of them as dots, but I think of it just like your phone. They're like pixels. So do this for me. This means I feel 100% comfortable about that. This means I really don't feel comfortable. You don't have to show everybody, just show me. You know what I mean? So how many are comfortable that when you look at this picture, you are seeing a whole bunch of dots? Like, can you imagine that really it's not lines, it's not curves, it's a bunch of dots, and they're so close together, they look like lines and curves, but they're really not. Like on an infinitesimal level, they're still all, there's an infinite number of them, so that's a little weird, but this means I'm comfortable. 1 is good, 0 is no. It's like a computer, 1 is yes, 0 is false. Everybody mark down a time mark for just voting, so cool. I'm going to get back to you, sorry. Hey look, so back to Noah's question. So what I'm trying to build on is this. Hey, look, you're all comfortable that it's a bunch of dots. You're all comfortable that those dots all next question. 1 or 0. Are you comfortable that every dot really represents 2 numbers? 1 or 0. Every dot represents 2 numbers. Every single dot on that board is representing 2 numbers. Mark down another one, okay? Rack them up. Okay, so we start there. Now we've got to go into a calculus concept, which is brand new. The idea of what they call a limit. It's just a mathematical word, somebody just invented it, but we've got to learn what that word means. Once you know what it means, using it isn't so hard. But if I do it the other way around, it's really difficult. Like if I just say, here's how you use it, don't worry about what it means, then you really struggle. So we're just starting with what this means. And when they throw on the word limit here, and they throw on this symbol, x arrow -1, your brain has to switch from thinking about x equaling -1. You can no longer think that. You got to think, no, x isn't -1. That's not the x I'm thinking of. I'm thinking of the x that's almost.
So I was just wondering, for the function, we're trying to find where the last coordinate is in the function. To find the continuity, we're going from where it starts to where it ends.
Oh.
And by finding the limit, we're finding the closest coordinate to the end of the function. Does that make sense?
The thinking is logical, it's just not what we're actually doing.
Okay.
So the way you put together the words and everything makes sense, it really does. It just happens to mean something else.
Okay.
So hold on, that will get there.
Okay.
2 more, good question. Yeah, so don't worry about continuity yet, that's going to show up in a little bit. Good question. Are you okay so far? Okay, back to here. 1 or 0 again. How many are comfortable that really, I can't pick a number? It's kind of a trick question. How many are comfortable that I can't really pick a number that is closer to -1 than this number inside the box. Show me 1 if that makes sense to you, 0 if it does not. Give a point for voting. So, I forgot your first name. Caleb Hughes?
Yeah.
Yeah, go ahead, Caleb.
So, I'm just trying to understand why we specified the number that it's very close to when what we're talking about is really just a concept and a different way of thinking.
Oh,
And why we need to use this for calculus to get the result.
so I'm going to try and give you kind of a short answer, and hopefully that's good enough for now, and as we go on, it will build. We encounter things down the road, not yet, where we really can't make a calculation when x is -1. It's impossible. But we can make a calculation when x is almost -1. And Isaac Newton proved that as long as we can get infinitesimally close, it's good enough. But that's not really much of an answer for now, but that's the best I can do for now. So it's going to show up later why this is important. Does that help a little?
Yeah.
2 more.
And like -1.000, like forever than 1, wouldn't work because you couldn't have an infinite number. Like that wouldn't be really close to it either because you just can't go on with the zeros forever. Is that right?
So, like that?
Yeah.
Kind of imagining that number.
Is it just that it's past it?
So I'm trying to manage names and calculus and all that stuff. So, Ellie Wagner, okay. Raise your hand if you were thinking of this number like Ellie. I gotta see. How many were thinking of that before she said it? 3 marked down, 2, Ellie gets 3. This number is just as infinitesimally close to -1 as this number. Yeah. I hadn't gotten there yet. I was hoping to get there. No, it's not the point. You led me right where I wanted to go. Yeah, I tend to really follow your questions, and I could see that we were kind of forgetting that there's really 2 ways to get close to -1. And I was pretty sure you guys would come to it. We just hadn't said it yet. That makes sense? So we started talking about this one, but we could have just as well talked about this one. One isn't more important than the other. They're just 2 different numbers that are both very close to -1. Please.
Yeah, so that was my question. It doesn't matter if you're going in a more positive direction or a negative direction?
It does not.
Why?
In reality, you have to check both. You can't, like when they say find a limit, you can't say, well, I'm not going to think of -1. You can't do that. You have to think of the number, the x value that is almost -1, but really I can't say that one of these is more important than the other, so I actually have to talk about both of them. That's kind of where we're at so far. Please.
Does that mean there's 2 answers?
Kinda, but correct. And I'm searching for your name, don't say it, I cannot remember it for nothing. Tell me again. Trey Robinson, thank you, there we go. 2 more for Trey, please.
Is there ever going to be a circumstance in which we would not have 2 approaching the number we want to get close to?
If you have x approaching infinity, which means you're just allowing x to get larger and larger and larger, then it's still considered a limit problem, but it's a different idea. It's not getting close to a number, it's just growing forever. 2 more.
Okay, that's actually kind of related to what I was asking. So this whole time you said like 0.999, it's almost -1, but is it like an asymptote where it's like approaching constantly, or are we just looking for -0.99, that single number?
Gotcha.
Like all the numbers leading into it.
2 more. I wouldn't think of it as an asymptote. I see why you're saying that, but I don't think that's particularly helpful. I would just think of it in terms of a number. That if I wrote the number 0.99999 and I could somehow do it forever, I would be representing a value that isn't -1, but it's certainly infinitesimally close to equaling -1.
So it is -1, but it isn't.
You cannot think of it as being -1 because it isn't. It's like they're distinctly different. You good with that?
Mm-hmm.
And it's Connor, yes?
Caleb.
Dang, sorry, we'll get there. Caleb Hughes. Okay, go please.
So we're trying to find the ways that we approach the -1 through positive and negative. It's like every way that you approach it.
You're trying to think, just think of it in terms of a list. So 2 for Liza. Look, if you were making a list of numbers, just counting, well, the number that comes just before -1 is this number.
Right.
Even though that's kind of not, I mean, because it goes on forever, that's a little bit hard to grasp.
Yeah.
But if I could somehow do it, that would be the number that would
Right.
come just before -1. And then this would be the number that would come just after
That would
-1.
approach it next.
Correct.
Okay.
Those are the 2 numbers. So approaching sometimes can be a little bit misleading. It's like, I just tend to think of it as, what are the 2 numbers that are most close to equaling -1, but neither one is actually exactly -1. That's how I think of it. Please.
Those repeating numbers, they don't technically have a point on the graph because they're getting infinitesimally closer to -1. So how is it like, I think probably everyone's struggling with the concept of like, how is it getting closer but not moving at the same time?
See if this helps a little bit. So if I'm looking at a graph and my eye is focused anywhere along this line here, every spot along that line has an x-coordinate of exactly -1. If I'm right here, I'm at an x-coordinate that is something a little bit more negative than -1. If I move to this dot, now I'm actually at an x-coordinate that is a little bit closer to -1. Now if I move to this dot, I'm at an x-coordinate that's even closer to -1. And you just have to imagine that you could keep doing that forever. You would never actually pick a dot whose x-coordinate is -1, but it's like you're following these dots and they go on forever. That's the part that's troubling, is that we're human beings. We live in a finite world. We're trying to talk about a concept that's infinite. That maybe helps a little.
Yeah, it's tough.
It is a little bit. 2 more, please.
So when we're talking about this, we're not talking about how, like, we're not talking about any of the points on the graph, we're just talking about what is closest to that number, and not like if there's a line on the graph, what point on that line is closest to that number.
I think it would help everyone. Look here, look. No, really good. Put 3 for that one. Think about, okay, I want to focus on what Taylor just said. I think the best place to start is don't pay attention to the graph yet. That kind of back to what Noah was saying. Don't pay attention to the graph. It's there because we're going to talk about it. Pay attention to just this. And just get clear in your mind that when it says limit as x approaches -1, like I said to Liza, you need to be thinking of 2 numbers. And those 2 numbers are -1.000 forever 1 and -0.99999 forever. And you should not be thinking of -1. That's where you begin. Now we're going to translate that and say, okay, how does that apply to whatever else we're looking at? Does that help a little?
Yeah.
Okay. I get that it's weird, just stay with me. Other questions? It feels like, I could be misreading the room, but it feels to me like most people are feeling a little better about just like ignoring everything else. Like when we say x approaching, we're going to vote again. When we say x approaching -1, if you're not comfortable, do this. If you're comfortable, do this. Are you comfortable that when you see this, your brain's going to say, I don't care what graph I'm looking at, I've got to be thinking of these 2 numbers. And I get that they're kind of pretend numbers because it's not really humanly possible to conceive of them. They go on forever. But the idea is pretty simple. It's like this number that's just barely less than -1, this number that's barely more than -1. So vote. Who's comfortable that when you see this symbol right there, that's what you should start thinking? And where we go from there, we're going to talk next. But we got everybody to that point. Cool. Awesome. Mark down a point for voting. And we got to see how many tallies I get. So how many tallies you have so far? Oh, sweet. We're doing good. Okay. Anybody else? Yeah, pretty good? Cool. Okay. Okay, next step. The numbers always come in pairs. So for any function, if there's an x-coordinate with this theoretical value, then there's a y coordinate that goes with it, always. It's always pairs. If there's an x coordinate with this theoretical value, then there's a y coordinate that goes with it. Are you comfortable? When they ask you to find a limit, they want you to find, don't say it, Trey Robinson, right? 2 more for Trey. Because you're the one who asked, was it 2 answers, right? And I kind of hedged and said, well, kinda. It starts out always as 2 answers, Trey, always. Like you've got to find, when it says this symbol right here, we've got to first think of, okay, what x are we thinking of? It's one of these 2, it's actually both of them. And now we've got to go find the y that goes here. That's why there's this symbol right here, F, telling us, hey, I'm going to tell you what x to think of. Your job is to go calculate what y. And back to Connor's question, Connor Hughes, yes?
Caleb.
Sorry, Caleb. Caleb Hughes. Caleb's question is, why would we even want to do that? That's going to show up in a few weeks. So for now, it's just a tool. There? Okay. Pretty good? Okay, now we go back to Taylor's question. 2 more for Taylor, which is, this picture is showing you all the xy values, all of them. But it's a picture, so it's kind of has human limitations, like I was saying to Noah. These dots go down forever. They don't really show that in the picture because they really can't, but they just keep going forever. And what you're trying to do is go find this x coordinate right here. Like somehow imagine that you could see the dot that has that x coordinate. So now we gotta raise our hands again. I'm not going to have you come to the board. That takes too long. We're always in a hurry in this class to get ready for May 13th. But raise your hand if you feel like you could actually come to the board, or you could, like I could walk up to your table and you could pick up your pencil and you could point. And you could point on the graph kind of roughly at the dot that is shown in the picture that has this x coordinate. Like you could kind of pretend to do that. With a picture, you can never actually do it, but you could kind of pretend. Show me hands. Who feels comfortable that you could do that?
Probably a trick question, but
Go ahead.
it's technically impossible to get that point since it's continually growing, and that concept of it is always true. But I suppose you could just point out where the line ends and say that's about where it is.
No, that's fair.
Even though it's just an estimate and it's very rough.
You are very correct. Like it is physically impossible for me to ever point at exactly this, like the dot that has that x coordinate. I really can't do it, but I can at least kind of imagine that I'm doing it by saying, okay, let's see. I'm supposed to pick an x coordinate, like a dot whose x coordinate is not exactly -1, but it's close. So I'm going to imagine that I just keep following these dots down, going further and further. They just keep going. Like I don't know where to stop. Like that's why I can't really do it, but I can kind of imagine doing it. Show me 1 or 0 if that made any sense. Everybody gets a point for voting. Talking about it, I didn't explain that very well.
I don't know, I just zoned out.
Oh, that's okay. No worries. No worries. Everybody good? Okay. So hands up again. Answer this. We're always talking about xy pairs. We said that when we're finding a limit, we're focused on the x that is not -1, but it's close. So back to Trey, we're focused on this x for now. Reggie, even tell me, for all these xy pairs that are depicted, what is the y that goes with this x?
Infinity.
Like,
Negative.
It's infinity.
is it positive infinite or negative infinite?
Negative.
How many knew that, hands? Point, good. Which isn't really a number, it's just an idea that it, like Caleb said, it would just keep going. The closer I picked x to equaling -1, but not quite -1, the closer the y value would get to becoming more and more negative.
I was going to say something kind of like that earlier, but I wasn't sure because there aren't arrows on the graph.
Oh, gotcha.
There are arrows.
That to me is just a flaw in the AP test. I'm not sure why they didn't put arrows. They should have. So you can feel free to draw that on if that helps, for sure. 2 more. For Josh. Anybody else? Ellenson. If I ever say your name wrong, please correct me. I don't want to memorize it wrong. So, yeah, please. Caleb.
Okay, and what about the other X points on this paper? Since they're not going indefinitely, like are they going indefinitely? No, like.
This one you would consider to keep going.
Yeah, but like.
The others do not. They're not.
Would we use the same like concept where it's a number that's super close to that point, but not the same point as for the ones that aren't continually growing, like
Two-
X equals 0?
2 more for Caleb. So that goes back to what I was saying to Noah, that we start by understanding what the notation means, and then we figure out how to apply it. And so, yeah, we're going to apply this to a lot of different situations. So far, we've applied it to one situation. Okay, back to here. Hands up. Oh, pause for a second. Nobody talk for a second. Hands up if you know what goes in this box. I gotta see if I get the whole room. What's gonna go here? How many knew it was positive infinity? Point? Okay, if you're not seeing it, just talk. Like it's just a matter of, you have to imagine, again, you have to imagine that you're looking at just dots on a board, and you're finding the right dot, and you're trying to see what the X and Y values are. That's all we're doing. Please, Alicia.
Are we referring to the asymptote right now, or like, because it's not like right on -1. I don't know if that makes sense. So I don't know what we're like.
Just keep talking, you're doing
I
great.
don't know.
Let me see if this helps, Alicia. Alicia Thomas, yes. Okay. And I always back up because I want to make sure we're coming from the same angle. So are you comfortable that when we see the board, just dots?
Yeah.
Good. Are you comfortable that every dot that is represented on the board, even though it's hard to draw, I can't really draw them all because there's infinite, they all represent an X and a Y?
Yeah.
Good. And they said, go investigate. Okay, this is where it's a little weird. If you look here, what I'm about to say is not mathematically perfect, but to me it's close enough to be helpful. There really is no single, Caleb has been saying this really well, there is no single dot that has this X coordinate, because you can just keep going forever and keep finding another dot. So I pretend that there aren't an infinite number. To me it's helpful just to think of it as like, well, this is the very last dot before I get to the one that has an X coordinate of -1. Like that's not really true, but it's helpful. Isaac Newton did this, not Isaac Newton, Albert Einstein did this all the time. Like he would think up examples that weren't perfect, but close enough to make sense of it. So we're gonna go to this dot. We're not gonna go to this one. Because there actually isn't one here. Because like you said, Alicia, that's the location of the vertical asymptote. Comfortable? But if I follow all the other dots, I would find one way down here that had an X coordinate of this number, right here, and the Y coordinate of that would be something extremely negative.
So we are following the arrow, like not the arrows, but we're following the lines.
What we're doing, you're doing great, just keep talking. It's such a good example of what I said, just talk and then I can help you figure it out. What we're doing is we are looking at all the dots and we're trying to find, of all those dots, which one is represented by this number here. And where I find it is I follow the dots and they just keep going lower and lower. That's better, yeah?
Yeah.
Yeah, and I say, well, I can't really go forever, but I'll just kind of pretend that I can. And the Y that would go with that X, so that X would be this. Does that feel good?
Yeah. Yeah.
And the Y would be something very negative. That's better, yes?
Yeah.
Perfect. Then when I go to this side, Alicia, I'm looking at the dots like going up this way because the X coordinate is slightly more than -1. Much better?
Yeah.
Mark down 3, please. Please,
So
Taylor.
when you talk about the dots, you mean like the dots, not just like every single dot on the graph, but the dots that are like the lines.
Yeah.
Let me say it back to you. You're doing great. Let me say it back to you. This board has a lot of dots on it. At this moment, I'm not looking at any of the dots over here. because none of those have an x-coordinate that's really near -1 at all. I'm looking for the dot whose x-coordinate can be represented by that number or that number. And where I find them is I find this one way forever down, and I find this one forever up.
Yeah.
Is that better?
Yeah, that makes, yeah, okay, I think I understand.
Better? Okay.
Will I ever reach -1?
When you're, everybody memorize this, look at me. Whenever you're finding a limit, you never ever think of x being -1.
Just theoretically, if the line goes forever, will it ever
Never.
reach -1?
Not when it's a vertical asymptote.
So -1 is essentially dead to us.
Okay? If you need, I put the flashcards on the desk because I think it's a very effective way to memorize key facts. If you don't like using flashcards, that's fine. Use whatever you like. But you need to somehow make a note that, like, summarize is the wrong word. Like, you need to make a note that reminds you that when you are finding a limit, you don't ever pay attention to this number. Don't ever, ever pay attention to that number. Like, you're always paying attention to the two numbers that are almost. These two here. Yeah, please.
Do the numbers that are almost -1, do they like get named?
Yes. And I'm searching for your name, don't say it. I always get stuck on your name.
Jared.
Jared Humphrey, sorry, Jared. If you look at a graph, Jared, this number here, is this on the right-hand side or left-hand side of -1? It's left-hand. So this is known as finding the left-hand limit. This is known as finding the right-hand limit. Two more for Jerry. Hazel, please.
If we were trying to find the y right and left hand limits for the second one, which isn't on the paper, it's the x approaching 1, wouldn't it have the same right and left hand limit?
In that case, yes. Sometimes that happens, sometimes it doesn't. But in that case, it would for sure.
Is there a way to write 1.0 being 1?
Yes. We write it like this. We say -1, August. Is this number more negative or more positive than -1?
Okay, it's more negative.
It's more negative. So we say it's -1, but it's slightly more negative than -1. So this is the valid mathematical symbol for this idea. Make sense?
Yeah.
Two more. Caleb,
So
you.
then, would the -0.9, would that be -1 with a plus sign next to it?
Two more. Because that number is slightly more positive than -1. It's perfect. It's perfect. Please.
Is that the answer, like in a coordinate? Would it be like just -1, negative, and then infinity?
That's where,
Two answers.
going back to Caleb again, because we're talking about numbers that are
Right.
not really numbers, you can't technically do this, but it's close enough for today.
Sure.
Yeah, close enough for today. Please.
You always have to find the right and left hand limits, or if they're the same, you just find one.
Okay, we look up. Three more for Spencer. You can tell that the points go up the more excited I get by that comment. So, I just had you make a note that when you're finding a limit, you absolutely cannot think of this number. You must think of the left-hand limit, and you must think of the right-hand limit. You cannot think of -1. Say your question one more time.
You have to find both right and left hand limits.
Every time you are finding a limit, you must always find both the left-hand limit and the right-hand limit. The only exception was the one I think Aisel brought up, where if x is approaching infinity, we use the word limit, but the meaning kind of changes. it's no longer getting close to anything. It's just x growing forever. But otherwise, if we're finding a limit with a finite number, we must always find, no exception, we must always find the left-hand limit and the right-hand limit. Grace, please. Oh, no, she's stretching again. Superb discussion, like really. Like if it feels a little weird, then welcome to Kevin. It's good. Yeah, no, it's fair. And that's why people always say this isn't math anymore. It's like, we're not doing anything, we're just talking, right? Yeah, well, that's because the AP test writers are so good at testing you on the theory. So I've got to help you understand the ideas, and then I can help you understand how to apply them. But the order has to be that order. Cool. Is that good?
Yeah.
And I can promise you one thing, look at me. It may feel weird on day one, but your brain far prefers to understand first. Like every human being on the planet, like I've never met a single person ever who didn't really want to understand something first rather than just follow instructions. Like it's boring to follow instructions, I hate it. Like I want to understand, once I understand, then I can apply. So, is that pretty good? Sweet, okay, cool. All right. We need to kind of reset. We've had a super good discussion. Now we're going to do some, so I didn't have you write anything on this, I just wanted you to listen. We've got a couple of key flashcards. One key flashcard is that when you're finding a limit, don't ever pay attention to the -1. Another key flashcard is that every single time you find a limit, you must find the left and you must find the right. Okay? You have to find the right-hand limit, you have to find the left-hand limit. Now we'll go back to Trey's comment. We're getting to his question. Once you have the two answers, Trey, you compare them. If they are the same, then the overall limit, which is that's what I call this thing, the overall limit has the same answer. So you just get one answer. If they are different, you say that the overall limit doesn't exist. That's just how limit is defined.
When you say you're comparing them, you're comparing the y value of the two limits, right?
Correct. So when we're finding the limit, 2 for Lincoln, we know what x we're supposed to be thinking of because they tell us. We're supposed to find, this x and this x. And then we use the data they give us to identify what y values go with them, because they're always in pairs, right here. And then we compare these numbers. And we say if those are the same, then the overall limit is that number. If those are different, then the overall limit does not exist. Please, Liza.
Will the y always be infinity of some kind?
No. Just in this particular example, it turned out to be. That's sometimes. Let's 2 more. Okay, let's get some notes on this now. So we're going to write some things on here now. So I'm going to erase the board. Good if I clear the board and start fresh?
Yeah.
Okay. So now we're going to talk about what Noah has been asking about. If this actually were like an AP question, it's not typically what they're going to have you do on an AP, but it's a good place to start. And they said, analyze the continuity of that function. I would start by writing, I've got to go find the limit. So go ahead and write this on your paper. You're going to need to fill up this box, so kind of squish it top left corner here. So you're going to write the limit as x approaches -1, and we're trying to find the limit of this function called f. So that's the first thing you would write on your paper. The notation is critical. If you don't have the right notation, they don't give you points. So, are we good? But as soon as I write that, I remember, oh, wait a minute, I can't really find that by itself. I've got to go find the left and the right limit. Sorry, I always say
No, you're good.
I have to go find the left and the right limit first. So now you're going to write below this, just making a little list here, the limit as x approaches -1 from the left. Like that. And then I'm hoping it's logical that the next line would be x approaching -1 from the right. questions? Okay, now I'm back to like what I was saying to Alicia. Now you're going to apply what we have talked about as far as like what all the symbols mean. So when I'm looking at this, I say, okay, I know what x I'm supposed to be thinking of. I'm supposed to be thinking of the x value that is this number here, negative 1.000 forever 1. That's the theoretical number I'm supposed to be kind of thinking of. And I'm supposed to go find, okay, x, y's, they always come in a pair. So what's the y that goes with it? We already found that out. It was just a number that becomes increasingly negative. Therefore, the value of this purple limit is negative infinite. The discussion day is superb. Like you do this every day until May 13th. I promise you'll kill the AP test. You will. Like you'll do so much better than you thought you could ever do. Promise. It's all it takes, just learning it the right way. So, questions? Well, so then this one we already figured out. This would be, you don't have to write the plus. I do it for emphasis. If you do it, it's not wrong. So it's up to you, but you don't have to. Questions about anything, please.
So a number can't something can't technically equal infinity. So is that just like a concept that?
That's really good. Take 3 for that one. It's Ellie. It's Mom?
Yeah.
Okay. No, that's actually right, Ellie. When we're finding it, and I'll be honest, I have to look that up. I can't remember. Like, because I get exactly what you're saying, that negative infinity isn't a number. It's this idea of growing forever. But I'm pretty sure I have seen mathematicians, like authors of math books, write it that way when they're talking about a limit. You would never say a certain value is equal to that. You'd have to say something like, oh, the y value is really just growing forever, right? It's the y value is approaching, it just keeps growing, But for the AP test, they're okay with that.
Okay.
It's a good question. Is everybody good? So don't say it out loud. 1 second. Just raise your hand if you know what I'm going to write here. Raise your hand if you know. At least check in the whole room. It's all good. There we go. Trying to pick on somebody I haven't called on yet. Don't say it. Maddox. Moss.
Yep.
Go ahead, Maddox.
Doesn't exist.
Does not exist. Wasn't quite as anonymous as I was hoping, but close enough. So, raise your hand if you honestly knew that before it was said. So give yourself a point. So we have a few that didn't. That goes back to if you need to make a flashcard. 1 second. Make a flashcard. When you're finding a limit, there's a sequence, and if you need to make a card that reminds you of this or make some notes in your notebook, whatever, you choose what's best for you. But that's the sequence of thoughts. Is you start with, okay, I know what x I'm supposed to be thinking of. Not -1, but close. So that led me to here. Now it says the F symbol here is telling me now go find the y value that goes with those x's. So I had to find the left and right limit. Once I find the left and right limit, I simply compare them. If they are identical, then my overall limit is the same as the left and right. If they are different, then the overall limit simply does not exist. Caleb, please.
Arbitrary does that get it?
Oh, this one here?
Yeah.
Awesome question. I forgot to explain that. We look up. 2 more for Caleb. Okay. Homework isn't something I ever collect. Homework is basically like notes for you. And it's just a bunch of problems to help you test and see if like what we talked about in class made sense. So that's why the homework is worth 5%. I actually give you every answer on every homework packet. So the way you should be treating homework is not doing homework. You should be using it like a little test. Where you say, hey, I'm going to test myself. I'm going to see if I can remember what we talked about. I'm going to do what I thought I was supposed to do. Then I'm going to look in the back and see if I did it. That's how you treat homework. So you keep this. This is for you forevermore. Like I'll never collect this. So. Other questions?
So
Please, Taylor.
If it is the same, then it's just like if, for example, the positive one was negative infinity, would the answer be negative infinity or just be the same?
2 more for Taylor and 2 more for Ellie Mon. that one's a little controversial in the mathematics world as well. Mathematicians can't quite agree. Some people say that if the limit is infinite, it really doesn't exist, because like Ellie said, it's not a number, it just keeps growing forever. But some people say it's like negative infinity. So if these were both negative infinity, some people will say this is negative infinity. And I like that method better because it's a little more precise. But some people would say it still doesn't exist because it's just negatively infinite. That's not a good answer, but that's the best I can do.
With the open dots on the thing, how do you, like, say for example, x equals 0 or something really close to 0, and the y value is at that line, or would it be at the dot?
So the dots that are, so the open circles are meant to represent that there's nothing there. We'll talk a little more about that in a minute, but please, Zach.
I was just looking at the answers, and like you kind of said, you could technically say they don't exist, but I mean, here says all three are non-existent, but would you rather us put the negative and positive infinity, or would you rather us say it does not exist for all three answers?
The AP test goes both ways, so I don't have a preference per se. As we're talking about in class, this method made more sense because it was easier for us to talk about it. The answers go the other way. Either way is fine. I don't have a preference because AP doesn't have a preference either. I guess a slight preference would be, I should probably change the key to be more like this, just because I think it's a little more precise as we talk about it. Not the best answer, but good enough for now. Two more, please, Taylor.
So for like the AP test, would you write that entire thing or just the top one?
Gotcha.
For your answer.
Gotcha. To be fair, to be honest, if they gave a question like this on an AP test, it would most likely be strictly multiple choice. This would not have been in the written section, and so you wouldn't need to write anything. You just have to think all three and come up with the correct answer.
But either answer does not exist, and
either one, they would take either one.
But if it's multiple choice and they're both answers, like
They won't give both answers. They'll give one or the other.
okay.
So I have seen cases where they'll say infinite is the answer. Other cases where they'll say does not exist is the answer. You have to interpret that they're both correct. They won't give both answers. Does that make sense? Yeah.
And they don't put the positive or negative sign.
This one here.
Like on the.
On this. This, if they put if they had negative infinity as an answer, that would be the correct answer. They wouldn't have these two as answers. Yeah.
So you're saying if those were both negative infinity, the answer would be either negative infinity or does not exist.
Correct.
And if they're different, then it just does not exist.
It has to be does not exist. That's very good. Everybody listen to what August just said. That's a good summary. Look up, look up, look up. That's a really good summary. If these two were both negative infinity, AP would accept two different answers for this one. You could write negative infinity, that would be correct. You could also write does not exist, that would also be correct. But with these both being different, there's only one choice here. It has to be does not exist. That's what you meant, yeah. Right. Two more, please.
So you just pointed out the hollow circles are holes in the graph, and I was wondering, like, when finding a limit on a graph, would it always be at a point that's either an asymptote or a hole in the graph?
Oh, excellent. Hold on. Everybody look up. Two more for Josh Ellertson. I would say on the AP test, about 95% of the time, if they ask you to find a limit, they are asking you to find a limit for a function at a spot of the function where the function either has a vertical asymptote, a removable discontinuity, which is also known as a hole, or a jump discontinuity. That's 95% of the time what they're going to be asking. About 5%, they'll try to trick you and ask at a place on the graph where nothing interesting is happening, just to see if you really understand what limit means. So, here we go. Okay, we got to stop for a minute. Okay, everybody look at me. To me, the discussion felt extremely productive. I follow you. Like every year I do this a little bit different. Every year I learn hopefully a little bit better how to help you understand it. I don't want you doing any homework yet, so there's no homework tonight. Like, put this in your binder, take it home, bring it back on Tuesday. We'll start discussing again. But I don't feel like we've done enough discussion to say, hey, go home and give it a shot. Like, don't. Just wait, come back, we'll talk about it again. Good job, you guys. Well done. Good job.